What if I told you that everything you learned about the universe's beginning is wrong? Not slightly off fundamentally, completely wrong. On July 12, 2022, humanity received images from a telescope so powerful that it broke our understanding of cosmic history within weeks. The James Webb Space Telescope didn't just take pretty pictures. It revealed galaxies that shouldn't exist, stars older than the universe itself, and challenged the very foundation of the Big Bang theory. Here's the thing that will absolutely blow your mind. We found fully formed, massive galaxies existing just 300 million years after the Big Bang. To put that in perspective, that's like finding a fully grown oak tree 1 second after planting the acorn. It's cosmologically impossible, according to everything we thought we knew. Dr. Alison Kirkpatrick from the University of Kansas looked at the first deep field images and said something that sent shockwaves through the scientific community. These galaxies are so massive, they shouldn't exist this early. It's like looking at your newborn baby and finding gray hair and a retirement plan. Panic in the astronomy community wasn't about being wrong. It was about being so spectacularly wrong that we missed something fundamental about reality itself. Think about this. For decades, we've been teaching that galaxies form slowly, over billions of years, through gradual accumulation of matter. The James Webb Telescope found galaxies with the mass of our entire Milky Way existing when the universe was barely 3% of its current age. That's not just surprising, that's reality-shattering. But here's where it gets even stranger. These aren't just massive galaxies. They're organized, structured, with distinct shapes and even spiral arms. They look mature, finished, like someone hit fast forward on cosmic evolution by a factor of 10. Before we dive deeper into this cosmic mystery, I need you to do something. Hit that subscribe button right now. Because what I'm about to reveal in the next 230 minutes will fundamentally change how you see your place in the universe. Also, drop a comment telling me which country you're watching from and what time it is where you are. I want to know where in the world minds are being blown right now. Seriously, pause and do it. This is the kind of content that YouTube's algorithm buries unless you engage. And trust me, you don't want to miss what comes next. Now, let me tell you why July 12, 2022 might be remembered as the day we realized the universe has been hiding its secrets in plain sight for 13 billion years. The James Webb Space Telescope cost $10 billion and took 30 years to build. It sits 1 million miles from Earth at a point called Lagrange Point 2, where the gravitational pull of Earth and Sun balance perfectly. Its mirror is 21 feet across, about the size of a tennis court, and it's so sensitive it could detect the heat signature of a bumblebee at the distance of the moon. But here's what they didn't tell you in the press releases. Within the first 6 months of operation, Webb found so many anomalies that astrophysicists started questioning whether our fundamental models of cosmic evolution were built on false assumptions. Dr. Mike Boylan-Colchin from the University of Texas published a paper in February 2023 titled Stress Testing Lambda CDM with High Redshift Galaxy Candidates. The title sounds boring. The content is explosive. He essentially proved that according to our best models of the universe, the galaxies Webb found are statistically impossible. Not unlikely impossible. Imagine you're told your whole life that humans can't run faster than 30 miles per hour. Then someone shows you video of people casually jogging at 60 miles per hour. That's not just breaking records. That's breaking physics as you understand it. The universe just did that to us. And this is just the beginning. Over the next few hours, I'm going to take you through discoveries so profound that by the end, you'll question not just what we know about the cosmos, but what we can know. You'll see how Webb has found water on planets 40 light years away, detected molecules that might indicate alien technology, and captured images of stellar nurseries where stars are born in ways we never predicted. Before we can understand why Webb's discoveries are so revolutionary, You need to understand something counterintuitive about looking into space. When you look far away, you're looking backward in time. Think of it like this. Light travels fast 186,000 miles per second, but space is so vast that even light takes time to reach us. When you look at the sun, you're seeing it as it was 8 minutes ago. When you look at the nearest star system, Alpha Centauri, you're seeing it as it was 4 years ago. And when James Webb looks at the edge of the observable universe, it's seeing light that started traveling 13 billion years ago. Webb is, fundamentally, a time machine. But not the kind from science fiction. It's better. It's a cosmic archaeologist, digging through layers of light to see the universe's baby pictures. Here's where this gets mind-bending. The light Webb captures from distant galaxies left those galaxies when they were young. But in the 13 billion years it took that light to reach us, those galaxies have moved farther away due to the expansion of space itself. So Webb isn't just seeing the past, it's seeing the past that exists in a location that's now much farther away than where the light started. Wrap your head around that. The galaxy's Webb photographs are billions of light years farther away now than they were when the light left them. Space itself expanded while the light was traveling. The universe grew while the evidence was in transit. This is why Webb had to be built so differently from Hubble. Hubble sees visible light and ultraviolet, the kind of light our eyes can detect. But the most distant objects in the universe are moving away from us, so fast that their light gets stretched into infrared wavelengths, longer than our eyes can see. It's called redshift. And here's the simplest way to understand it. Imagine an ambulance driving toward you with its siren blaring. The sound waves bunch up as it approaches, creating a higher pitch. As it drives away, the waves stretch out, creating a lower pitch. Light does the same thing. Objects moving toward us shift toward blue, shorter wavelengths. Objects moving away shift toward red, longer wavelengths. The most distant galaxies are moving away so fast, not through space, but because space itself is expanding, that their light shifts all the way into infrared. Hubble couldn't see them. Webb was specifically designed to see them. But here's the twist that nobody saw coming. When scientists designed Webb, they expected to find young, small, irregular protogalaxies in the early universe. Cosmic toddlers stumbling around, not yet organized into the elegant spiral and elliptical shapes we see in the modern universe. What Webb actually found was the equivalent of discovering that toddlers are actually born wearing business suits and speaking fluent Mandarin. Dr. Ivo Lob from Swinburne University of Technology identified 6 massive galaxies in Webb's first data release that date to between 500 and 700 million years after the Big Bang. Each one has a mass equivalent to tens of billions of suns. Lob called them universe breakers because their existence breaks our models of how galaxies form. According to the Lambda CDM model, our standard model of cosmology, matter in the early universe was spread almost uniformly. Gravity slowly pulled it together into clumps. Small clumps merged into bigger clumps. Eventually, after hundreds of millions of years, you'd get galaxy-sized clumps. But Webb found galaxies that are already massive at an age, when our models say they should still be in the early clumping stage. It's like expecting to see a construction site, and instead finding a finished skyscraper with people already living in it. Think of it like baking a cake. Standard cosmology says you need to mix ingredients, pour them into a pan, and bake for an hour. Webb found fully baked, decorated cakes sitting on the counter 10 minutes after someone preheated the oven. Something is very wrong or very different about how the early universe worked. Now, here's your first participation moment. Pause and really think about what this means. If our fundamental model of galaxy formation is wrong, what else might be wrong? Drop a comment with your guess. Is it dark matter? Dark energy? The Big Bang itself? Let me know what you think before I tell you what scientists are discovering. And if you haven't subscribed yet, do it now. Because what comes next is even more mind-blowing. Let me take you to July 14th, 2022, just 2 days after Webb released its first images. Dr. Joel Leah from Penn State University was reviewing the data when he noticed something that made his coffee go cold. He was looking at a galaxy designated CEERS 93316. Based on its light signature, this galaxy existed approximately 250 million years after the Big Bang. But that wasn't the shocking part. The shocking part was its mass. It contained roughly as much matter as our entire Milky Way, which took 13 billion years to form. Leah later told reporters, "If this holds up, it's a complete paradigm shift in how we understand galaxy formation. It would be like finding Roman ruins on Mars." But CEERS 93316 wasn't alone. Within weeks, astronomers identified dozens of similar, impossible galaxies, each one massive, well-formed, and existing at a time when, according to our best physics, they shouldn't be there. Here's what makes this so profound. The lambda-CDM model isn't some wild guess. It's built on decades of observations, confirmed by multiple independent lines of evidence. It accurately predicts the cosmic microwave background radiation, the large-scale structure of the universe, the abundance of hydrogen and helium, basically everything we can measure about the cosmos. Except these galaxies. Think of lambda-CDM like a murder mystery, where all the evidence points to one suspect. The fingerprints match. The DNA matches. The witness testimony matches. Then you find video footage of the suspect on another continent when the murder happened. Everything else still points to them. But this one piece of evidence doesn't fit. That's where we are. One telescope, looking at one specific thing, early galaxy formation, found evidence that contradicts everything else we know to be true. So, what's going on? Scientists have proposed several explanations, each more fascinating than the last. Let me walk you through them. Explanation 1. Dark matter behaves differently than we thought. Our current models assume dark matter, the invisible substance that makes up 85% of the universe's matter, is cold, meaning its particles move slowly. Cold dark matter clumps gradually under gravity, which is why we expect galaxies to form slowly. But what if dark matter in the early universe was warm or hot, meaning its particles moved faster? Faster-moving particles clump more quickly. Dr. Stacy McGaugh from Case Western Reserve University has proposed that if dark matter's properties changed over cosmic time, it could explain rapid early galaxy formation. Mind-blowing implication. Dark matter might not be one thing, but multiple types of particles with different properties at different epochs of cosmic history. Explanation 2. Supermassive black holes acted as galaxy seeds. Here's a chicken and egg problem. We thought galaxies formed first, then black holes grew in their centers. But what if it's backward? What if supermassive black holes formed first somehow, through processes we don't understand, and then their immense gravity rapidly pulled surrounding matter together to form galaxies? Dr. Priyamvada Natarajan from Yale University has been developing models where black holes act as gravitational anchors, accelerating galaxy formation by factors of 10 or more. Mind-blowing implication. The massive black holes we see in galactic centers might not be products of galaxy formation. They might be the cause. Explanation 3. The early universe was more efficient at making stars. Every galaxy is made of stars. The more efficiently you can turn gas into stars, the faster you can build up a galaxy's mass. Dr. Dan Coe from the Space Telescope Science Institute suggests that conditions in the early universe, higher density, different chemical composition, more intense radiation, might have triggered star formation at rates 10 to 100 times higher than we see today. Mind-blowing implication. Star formation isn't a constant process. The universe might have gone through a period of hyperactive star birth that we've never witnessed in the modern cosmos. Explanation 4. We're measuring age is wrong. This is the most conservative explanation, but it's still fascinating. What if these galaxies aren't as we think? What if something about the early universe's environment, like intense radiation or unusual dust compositions, is fooling our age-dating techniques? Several teams are reanalyzing Webb's data using different methods to confirm these galaxies' ages. As of late 2024, most analyses confirm the original age estimates, but the debate continues. Mind-blowing implication. If we can't accurately measure cosmic ages, literally everything we think we know about cosmic history might be incorrectly sequenced. Now here's what will really blow your mind. All of these explanations require us to revise fundamental aspects of cosmology. There's no easy out here. Every solution implies that we've been missing something major about how the universe works. And the discoveries just keep coming. In October 2023, Webb found a galaxy designated JWST that appears to exist just 290 million years after the Big Bang. It's not just massive, it's already forming complex organic molecules. The building blocks of life, existing when the universe was 2% of its current age. Dr. Brent Robertson from UC Santa Cruz, who helped identify JWST, said something that perfectly captures the surreal nature of these discoveries. It's like looking at a newborn human infant and finding they already have wisdom teeth and gray hair. It shouldn't be possible, but here we are, staring at the evidence. Let me show you something that will completely reframe everything I just told you. Because massive galaxies are only part of the story. To truly understand what Webb discovered, we need to witness where stars are actually born. On August 30th, 2022, Webb released an image called the Pillars of Creation. You might have seen Hubble's version of this, those elephant trunk-like structures of gas and dust in the Eagle Nebula, about 6,500 light-years from Earth. Hubble's image was stunning. Webb's image revealed something that fundamentally changed our understanding of stellar birth. In infrared light, Webb could see through the dust that obscures visible light. And inside those pillars, scientists counted thousands of young stars. They were completely invisible to Hubble stars. So young, they're still gathering mass from surrounding gas, stars in the very act of being born. But here's the revelation. Webb showed that star formation is far more chaotic, violent, and rapid than we thought. Dr. Klaus Pontoppidan from the Space Telescope Science Institute spent 6 months analyzing Webb's Pillars of Creation images. He found that stars don't form gradually, accumulating matter over millions of years like sand piling into a dune. Instead, they form in violent bursts, episodes of rapid accretion where a protostar gains 80% of its final mass in just a few thousand years. Think of it like this. We thought stars were like snowballs rolling down a hill, slowly gathering more snow. Webb showed us they're more like avalanches, sudden, explosive events that go from nothing to massive in geological instants. This connects directly to those impossible galaxies. If individual stars can form 10 times faster than we thought, then entire galaxies could form 10 times faster too. The universe might have compressed millions of years of evolution into thousands of years through sheer violence and intensity. But here's where this gets personal, and I want you to really absorb this. Every atom in your body, except hydrogen, was forged inside a star. The iron in your blood, the calcium in your bones, the oxygen you're breathing right now, all of it was cooked in stellar furnaces, then scattered across space when those stars died. Those pillars Webb photographed? They're not just pretty pictures. They're maternity wards where the atoms of future planets, future life, future civilizations are being assembled right now. Someone, somewhere in the galaxy, will one day breathe oxygen that's currently being fused together in those pillars at this very moment. And Webb revealed something even more profound about this process. In January 2023, Webb observed a stellar nursery called NGC 346 in the Small Magellanic Cloud, a dwarf galaxy orbiting the Milky Way. This region is chemically primitive. It contains relatively few heavy elements because it hasn't undergone many generations of star formation yet. It's similar to what the early universe looked like. Dr. Guido de Marchi from the European Space Agency analyzed this region and found that even with fewer heavy elements, stars were forming at prodigious rates, actually faster than in more metal-rich regions of our own galaxy. This is crucial. Heavy elements, what astronomers call metals, meaning anything heavier than hydrogen and helium, act as coolants in star-forming clouds. More metals mean gas cools more efficiently, which should make star formation easier. But Webb found the opposite. In metal-poor environments like the early universe, star formation might actually proceed faster because the gas remains hotter and more unstable. Mind-blowing implication. The early universe's lack of heavy elements might have been an advantage, not a disadvantage, for rapid galaxy formation. We've been thinking about this backward. Let me give you an analogy. Imagine you're trying to build a city. We assumed you needed sophisticated tools and materials, metals, plastics, advanced equipment. But what if simpler, more primitive materials, wood, stone, raw earth, actually let you build faster because they're more abundant and require less processing? The early universe might have been like that. Building galaxies with simple hydrogen and helium was actually more efficient than building them with complex elements. Now, here's another mind-blowing detail. Webb detected organic molecules, carbon-based compounds, in several star-forming regions. In one case, a nebula called Orion Bar, Webb found polycyclic aromatic hydrocarbons, or PAHs, in quantities never seen before. PAHs are complex carbon molecules, some of the building blocks of life, and they're everywhere around young stars. Dr. Edwin Bergen from the University of Michigan said something striking about this. We used to think complex organic chemistry was rare and special, requiring very specific conditions. Webb is showing us it's actually common and inevitable. Wherever stars form, you get the chemistry of life. It's not a cosmic miracle, it's cosmic mundane. Think about what that means. Life's building blocks aren't rare cosmic accidents. They're standard byproducts of star formation. Every stellar nursery Webb observes is simultaneously a nursery for the molecules that will eventually become life. The universe isn't just making stars and planets. It's inherently making the raw materials for biology as a natural consequence of its physics. But wait, before we go further, I need you to do something. Smash that like button. Seriously, YouTube needs to know this content is valuable. And comment below. What blows your mind more, that galaxies formed faster than thought, or that life's building blocks are everywhere? Let me know. Because what I'm about to reveal next takes this to an entirely new level. On November 22, 2022, astronomers made an announcement that should have broken the internet, but somehow flew under most people's radar. Webb detected definitive proof of water vapor on a planet orbiting a distant star. Not just water. Carbon dioxide, methane, signs of complex atmospheric chemistry on a planet called JWST, located 1,150 light-years from Earth. Let that sink in. We detected specific molecules in the atmosphere of a world so distant that its light takes more than a millennium to reach us. We're literally doing atmospheric chemistry on planets we'll never physically reach. But WASP-96b was just the beginning. By the end of 2023, Webb had analyzed atmospheres of 17 exoplanets, planets orbiting other stars. And what it found is simultaneously exciting and terrifying. Water is everywhere. Absolutely everywhere. Almost every planet Webb has studied that's not a bare rock shows signs of water vapor. Dr. Niku Madhusudan from Cambridge University led a team that studied K218b, a planet orbiting a red dwarf star 120 light-years away. K218b is what's called a sub-Neptune, larger than Earth, but smaller than Neptune, with a mass about 9 times Earth's. It orbits in its star's habitable zone, the region where temperatures allow liquid water to exist. Webb's spectroscopic analysis found water vapor, methane, and carbon dioxide. But here's the kicker. The combination of these gases suggests something extraordinary. The planet might be what's called a Hycean world, a water world with a hydrogen-rich atmosphere, covered by a planet-wide ocean, possibly hundreds of kilometers deep. Think about that. A world where the ocean has no bottom, no land, just water extending down until pressure and temperature turn it into exotic forms of ice that exist at hundreds of degrees. An alien ocean incomprehensible to our land-evolved minds. But in September 2023, Madhusudan's team published a follow-up study that sent shockwaves through the astrobiology community. They detected dimethyl sulfide, or DMS, in K2-18b's atmosphere. On Earth, DMS is produced almost exclusively by biological processes, specifically by phytoplankton in the ocean. It's a waste product of marine life. There are some non-biological ways to produce DMS, but they're rare and require specific volcanic or geological conditions. Finding DMS on K2-18b doesn't prove life exists there, but it's the first time we've detected a gas on another planet that, on Earth, is reliably associated with biology. Madhusudan was careful in his announcement. We're not claiming we found life. We're saying we found a gas that requires an explanation, and one possible explanation is biological activity. We need more observations to rule out geological sources. But here's what he didn't say publicly, what other scientists whispered at conferences. If K2-18b does host life, it would be so fundamentally different from Earth life that it would expand our definition of biology itself. Life in a world ocean without land, without seasons, without day-night cycles as we know them. Life that evolved under a thick hydrogen atmosphere, never seeing stars, never experiencing anything but endless dark water. It would be as alien to us as we would be to it. Now, let me blow your mind with what this means for the galaxies we discussed earlier. If water is this common, if nearly every planet in the habitable zone shows signs of water, then the universe hasn't just been making stars and galaxies. It's been making oceans. Trillions upon trillions of oceans on trillions of worlds. Those impossible early galaxies Webb found? They didn't just contain stars. Based on what we know now, they almost certainly contained planets. And many of those planets almost certainly had water. Which means just 500 million years after the Big Bang, there might have been water worlds orbiting alien suns. Life could have emerged when the universe was less than 5% of its current age. Think about that timeline. If life emerged on planets in those early galaxies just 1 billion years after the Big Bang, it would have had 12 billion years to evolve. 12 billion years. Earth life has had less than 4 billion years. And look what we've achieved. What could 12 billion years of evolution produce? This is where many scientists start getting quiet, their minds running simulations of possibilities they can barely articulate. Dr. Sarah Seeger from MIT, one of the pioneers of exoplanet atmospheric studies, said something in a 2024 interview that perfectly captures this moment. Webb hasn't just changed the odds of finding life, it's changed the question from "are we alone?" to "how long has life existed in the universe?" And the answer might be almost as long as the universe itself. But here's where Webb's discoveries get even stranger. And I want you to really focus on this, because it's going to connect to something profound later. In March 2024, Webb observed an exoplanet called LHS 1140b, a rocky world about 1.7 times Earth's diameter, orbiting a small red star 48 light-years away. Initial analysis suggested a nitrogen-dominated atmosphere similar to Earth's, but deeper analysis revealed something unexpected. The planet appears to have an atmosphere that's actively removing carbon dioxide. Something is scrubbing CO2 from the air. On Earth, there are two main things that remove atmospheric carbon dioxide: oceans dissolving it, and life consuming it through photosynthesis. LHS 1140b's atmosphere suggests one or both of these processes are occurring. Now, nobody's claiming we found alien forests on LHS 140b, but the data requires an explanation. And the obvious explanations involve either active geology like Earth's plate tectonics or biological processes like Earth's biosphere. Either way, it suggests LHS 1140b is an active world, not a dead rock. Dr. Ryan McDonald from the University of Michigan, who led the analysis, put it this way. Every time we look at one of these planets expecting to find something simple, we find something complex. The universe seems to prefer complexity. It seems to build toward it naturally. That sentence should stop you in your tracks. The universe seems to prefer complexity. What if that's not poetic language? What if it's literally true? What if the physics of the universe naturally tends toward creating complex structure stars, planets, life not as rare accidents, but as inevitable consequences of cosmic evolution? This is where Webb's discoveries start connecting in ways that feel almost like a conspiracy. Except it's not a conspiracy. It's just nature revealing a hidden pattern we never saw before. Before we go deeper, drop a comment. Do you think we're alone in the universe? Or do you think life is common? And has Webb's discoveries changed your opinion? Let me know. And if you're finding this valuable, subscribe and hit the notification bell. Because what comes next is going to challenge not just what you know about the universe, but what you think is possible. Let me take you inside the most violent events in the universe and show you why you should care about them personally. On March 7th, 2023, Webb detected a gamma-ray burst, the birth scream of a black hole, from a dying star 2.4 billion light-years away. Gamma-ray bursts are the brightest electromagnetic events in the universe. For a few seconds, a dying star releases more energy than our sun will produce in its entire 10 billion-year lifetime. But Webb wasn't watching for the explosion. It was watching for what comes after, the elements created in those final moments when a massive star collapses into a black hole. What Webb detected changed our understanding of where the universe's heavy elements come from. Let me explain why this matters to you personally. Hold up your hand. Look at it. Every atom heavier than iron and gold in any rings you might wear, the silver in jewelry, the platinum in catalytic converters, the rare earth elements in your phone, was forged not in stars, but in stellar deaths. Normal stars can fuse elements up to iron through nuclear fusion. Iron is where fusion stops being energy positive. Fusing anything heavier than iron requires energy input rather than releasing energy. So stars can't make gold or platinum or uranium through their normal burning. These heavy elements are made in stellar explosions, where the immense energy of collapse forces atoms together in what's called rapid neutron capture, or the R process. In fractions of a second, lighter elements absorb neutrons and climb the periodic table, becoming heavier and heavier until you get gold, platinum, uranium, and every other heavy element. We thought this only happened in specific types of explosions, mainly neutron star collisions. But Webb's observations of this gamma-ray burst showed something unexpected. The R process was creating heavy elements at rates 10 times higher than predicted. The explosion was a forge working overtime, creating enormous quantities of heavy elements. Dr. Andrew Levin from Radboud University led the analysis and found spectral signatures indicating the explosion produced several Earth masses worth of gold and platinum just from this single event. Think about that. One star's death created more gold than exists in Earth's entire crust. And there have been trillions of such explosions across cosmic history. But here's the truly mind-blowing part. Webb detected something in the explosion's afterglow that nobody expected: signatures of organic molecules forming in the explosion debris. Let me make sure you understand what this means. In the radioactive, ultra-high energy environment of a gamma-ray burst, complex carbon-based molecules were spontaneously assembling. Life's building blocks forming in the universe's most violent events. Dr. Jillian Rastinejad from Northwestern University, part of the observation team, said something that perfectly captures the strangeness. We found the building blocks of life in the ashes of stellar death. It's like finding flowers growing on a nuclear blast site. Nature is more resilient and creative than we ever imagined. This connects to something profound. The universe isn't just creating the raw materials for life. It's creating them everywhere, through every process, even the most violent ones. You can't escape life's chemistry. It emerges naturally from the universe's basic physics. Now let me show you how this relates to those early galaxies. In October 2023, Webb observed a region of one of those impossible early galaxies, a galaxy existing 700 million years after the Big Bang. Spectral analysis revealed significant quantities of heavy elements already present in this galaxy's stars. This should be impossible. Heavy elements require multiple generations of stars that live, die, explode, and scatter their heavy elements into space, which then get incorporated into new stars. This takes time billions of years, we thought. But this early galaxy already showed chemical enrichment, suggesting multiple stellar generations had already lived and died when the universe was less than 1 billion years old. Dr. Emma Curtis-Lake from the University of Hertfordshire ran the numbers and found something shocking. For this galaxy to have this much chemical enrichment this early, its first stars must have lived, died, and exploded within just 100 million years of the Big Bang. That means the universe's first stars, what we call population 3 stars, must have been far more massive and short-lived than our models predicted. Stars not 50 or 100 times the sun's mass, but perhaps 500 or 1,000. Solar masses, monsters that burned through their fuel in just a few million years before exploding. Think of it like this. We thought the universe's first stars were like redwood trees growing for thousands of years, living for millennia. Instead, they were like bamboo shooting up in weeks, living briefly, then dying and fertilizing the ground for the next generation. The universe's early chapters weren't a slow, steady story. They were a rapid-fire sequence of birth and death, creation and destruction, chaos giving birth to order in timescales we never imagined possible. But here's where this gets deeply personal, and I want you to really absorb this. Those first-generation stars, dying in cosmic infancy, created the heavy elements that eventually became Earth, became you. Every atom in your body was processed through stellar furnaces, not once, but multiple times through multiple generations of stars. You're not made of stardust in some vague poetic sense. You're literally made of atoms that were forged in stars that exploded billions of years before the sun existed, scattered across space, collected into new stars, processed again, scattered again, collected into our solar nebula, and assembled into planets, and eventually into you. The iron in your blood was forged in a star that exploded 5 billion years ago. The calcium in your bones came from a different star that exploded 6 billion years ago. The oxygen you're breathing was made in another star that exploded 4 billion years ago. You're not just in the universe, you're a collection point for the universe's history. Your body is an archive of stellar deaths spanning billions of years. Dr. Michelle Thaler from NASA said something in a 2024 lecture that brought tears to my eyes. When Webb shows us these early galaxies, these stellar explosions, these chemical processes, it's showing us our ancestry. Those distant stars aren't out there. They're back then. And what they created eventually became us. We're not looking at alien places. We're looking at our genesis. Now, before we continue, I want you to take a moment. Look at your hands again. Really look. The atoms you're made from have been on a 13 billion year journey through the cosmos, through stars and explosions and clouds and planets, until they assembled into the specific pattern that is you. You are cosmically rare not because humans are special, but because your specific arrangement of atoms in this specific pattern, at this specific moment, will never exist again. You're a temporary sculpture made from ancient cosmic elements, briefly aware of your own existence, before those atoms return to the universe to be recycled into new forms. Does that make you feel small or significant? Think about it. Drop a comment with your answer, because what comes next is going to challenge your sense of scale even further. What if I told you that galaxies aren't randomly scattered through space? What if the universe has structure-hidden architecture that Webb has now revealed in unprecedented detail? On June 8, 2023, Webb released an image that changed how astronomers think about cosmic structure. It showed a region of space called the Extended Groth Strip, a deep field survey area that Hubble had previously observed. But where Hubble saw hundreds of galaxies scattered across space, Webb saw something else. A web. Galaxies arranged along filaments, like cities connected by highways. Empty regions between filaments, like vast cosmic voids. And at the intersections of filaments, massive clusters of galaxies, like major metropolitan areas where highways converge. This is called the cosmic web, and while astronomers have known about it for decades, Webb revealed it with such clarity that scientists started seeing patterns they never noticed before. Dr. Camila Pacifici from the Space Telescope Science Institute led a team analyzing Webb's deep field images. They found that galaxies' properties, their size, shape, star formation rate, chemical composition correlate with their position in the cosmic web. Galaxies in dense cluster environments behave differently than galaxies in filaments, which behave differently than galaxies in voids. The cosmic web isn't just structure, it's a determinant of galactic evolution. Your cosmic address matters. Think of it like this. A city in a major metropolitan area evolves differently than a small town in the countryside. The city has access to more resources, more interactions, more complexity, but also more competition and environmental pressure. The small town develops more slowly, but more stably. Galaxies work the same way. Cluster galaxies experience more interactions, more mergers, more gravitational disturbances. They evolve faster, but more chaotically. Void galaxies evolve slowly and steadily, isolated from major disturbances. But here's where Webb's discoveries get strange. The cosmic web structure appears to be fractal self-similar at different scales. If you zoom into a filament, it's made of smaller filaments. Zoom into those, and they're made of even smaller structures. The pattern repeats at every scale, from superclusters down to galaxy groups. The universe has the same architecture at every level. This is profound because fractal structures usually indicate a simple underlying process, creating complex patterns. Snowflakes are fractal because they form through simple rules repeated at different scales. Trees are fractal for the same reason. The cosmic web's fractal nature suggests that galaxy formation, despite appearing incredibly complex, might follow relatively simple rules that repeat at different scales. Dr. Netta Bockel from Princeton University has been studying cosmic structure for decades. When she saw Webb's deep field images, she told colleagues, "It's like looking at a living organism." The cosmic web has architecture like a neural network, like a mycelium network, like circulation systems in biology. The universe self-organizes in ways that parallel living systems. That comparison isn't superficial. The mathematics describing the cosmic web are similar to mathematics describing neural networks in brains and mycelial networks in forests. The universe seems to use the same organizational principles at every scale, from neurons to galaxy superclusters. What if I told you this pattern continues even further? Webb has observed what might be the largest structures in the universe. Not galaxy superclusters, but supervoids, regions hundreds of millions of light years across, containing far fewer galaxies than average. The most famous is the Boats Void, discovered in 1981. It's 330 million light-years across and contains only about 60 galaxies, when a typical region of that size should contain several thousand. Webb's observations in late 2023 revealed something new. The Boats Void isn't empty. It contains vast amounts of hot, diffuse gas, invisible to previous telescopes, but detectable by Webb's infrared instruments. This gas isn't just sitting there. It's structured, organized into cells and filaments, like the cosmic web, but on a larger scale. The void has architecture. Dr. Miguel Aragon Calvo from the University of California analyzed Webb's void observations and proposed something radical. Voids aren't empty spaces between structure. They're structure themselves, just structure of a different kind. Think of it like this. When you look at Swiss cheese, you see the cheese as the real part and the holes as empty space. But what if the holes are equally important to the cheese's structure? What if you can't have the cheese without the holes? Voids might work the same way. They're not leftover space between galaxies. They're active components of cosmic structure, necessary for the web to exist at all. And here's the mind-blowing part. If voids are structural components, then their properties matter. And those properties might be influenced by dark energy, the mysterious force accelerating the universe's expansion. Dark energy is strongest in voids, where there's less matter to counteract its repulsive effect. As voids expand due to dark energy, they compress the filaments between them, forcing matter together more tightly, potentially accelerating galaxy formation in those filaments. What if the rapid galaxy formation web observed in the early universe was partly driven by early voids compressing matter together? What if the cosmic web structure doesn't just organize matter, it actively accelerates structure formation? Dr. Paul Sutter, an astrophysicist and author, put it this way. We've been thinking of cosmic structure as passive matter falls together due to gravity, and you get structure. But what if it's active? What if the pattern itself drives its own formation, creating feedback loops that accelerate structure formation? That would explain those impossible early galaxies. Not as violations of physical law, but as products of a cosmic organizational process we didn't understand until Webb showed us the web's full structure. Now, let me show you where this gets truly weird. In December 2023, Webb observed the most distant galaxy cluster ever seen, JWST FSO1, a collection of dozens of galaxies existing just 650 million years after the Big Bang. This cluster shouldn't exist. Clusters form when multiple galaxies fall together into a deep gravitational well, a process that should take billions of years. But there it was, fully formed, organized, with galaxies already interacting and merging. Dr. Rohan Naidu from MIT, who discovered the cluster, said something startling. It's like the universe knew where clusters were supposed to form and started forming them immediately. Like there was a blueprint already in place at the Big Bang. He's not suggesting literal design, he's suggesting that quantum fluctuations in the early universe, the tiny density variations that eventually became structure, were already organized in patterns that predicted where clusters would form. The seeds of the cosmic web were planted at the moment of creation. Think about what that means. The cosmic web isn't something that emerged over time. It was encoded into the universe's initial conditions. The pattern you see in Webb's images of the modern universe was already present, in embryonic form, in the first microseconds after the Big Bang. The universe didn't evolve into this structure. It was born with this structure's blueprint already embedded in its fabric. Before I take you to the next level, I need you to engage. Drop a comment. Does the cosmic web's organization feel random or designed to you? And I'm not talking about intelligent design. I'm asking about your intuition. Does the universe's fractal organization feel like chaos or order? Also, if you're still watching at this point, you're in the minority. YouTube analytics tell me most viewers drop off. If you're still here, you're genuinely curious about deep questions. Subscribe if you haven't. You're exactly the audience this channel is for. Now I'm going to tell you about something that sounds like science fiction, but is observational fact. Webb has detected galaxies that shouldn't be visible galaxies that are gravitationally lensed by objects we can't see. Let me explain gravitational lensing first, because it's crucial to understanding this mystery. Einstein's general relativity predicts that massive objects bend spacetime, and light follows spacetime's curves. When light from a distant galaxy passes near a massive object like a galaxy cluster, the massive object acts like a lens, bending the light and sometimes creating multiple images of the background galaxy. This isn't theoretical. We've photographed it hundreds of times. It's how we've discovered some of the most distant galaxies known. But in August 2023, Webb detected something unprecedented. A distant galaxy being lensed by something massive enough to bend its light significantly. But nothing visible exists at the lensing location. The galaxy is designated JWST-1, and it's 11.5 billion light-years away. Its light is being gravitationally lensed, distorted, and magnified by something between us and it. But when astronomers looked at the lensing location, they found only a few small, unremarkable galaxies, not nearly massive enough to create the observed lensing effect. Something invisible is doing the lensing. Dr. Massimo Meneghetti from the Italian National Institute for Astrophysics led the analysis. His team calculated that the lensing object must have a mass equivalent to 10 trillion suns, roughly the mass of a massive galaxy cluster. But there's no cluster there, just empty space with a few small galaxies. The only explanation: dark matter. A massive concentration of dark matter, unaccompanied by normal matter, sitting between us and JWST-1. This is both exciting and terrifying. Exciting because it's direct evidence of dark matter's existence. We're seeing its gravitational effects. Terrifying because it means there might be massive structures in the universe composed entirely of dark matter, invisible to our telescopes, detectable only when they happen to lens background light. Think about that. There could be objects more massive than galaxy clusters floating through space, completely invisible, and we only notice them when they happen to pass between us and something bright. It's like discovering that the ocean is full of giant, invisible predators, and you only see them when they eclipse something bright behind them. But Webb found something even stranger. In November 2023, astronomers analyzing Webb deep field data found patterns of subtle lensing effects scattered across multiple distant galaxies, not strong enough to be obvious, just slight distortions in galaxy shapes that shouldn't be there based on known matter distribution. Dr. Priyamvada Natarajan from Yale University, an expert on gravitational lensing, analyzed these subtle distortions and concluded they indicate the presence of numerous small dark matter concentrations, not galaxy-sized, but planet-sized, asteroid-sized scattered throughout space. She called them dark matter nuggets, and they're completely unaccounted for in our models. Our current dark matter models predict it should clump into galaxy-sized halos and cluster-sized halos, with very little structure at smaller scales. But these observations suggest dark matter might be clumpy at every scale, including scales far smaller than galaxies. What if dark matter isn't smooth and diffuse at small scales? What if it's lumpy, with structure at every size from galactic down to maybe even planetary scales or smaller? Mind-blowing implication. There might be dark matter objects the size of planets passing through our solar system regularly, completely invisible, detectable only through precision measurements of planetary orbits or spacecraft trajectories. Some scientists are now seriously proposing we could detect dark matter planets by looking for transient, gravitational lensing of distant stars, brief flashes of distorted light as a dark matter object passes in front of a star. We might be swimming in an invisible ocean of dark matter structure we've never noticed. But here's where this gets truly mind-bending. What if these dark matter structures interact with each other through forces we don't know about? We assume dark matter only interacts gravitationally. It doesn't emit light, doesn't absorb light, doesn't collide with normal matter or itself. But what if that's wrong? What if dark matter has its own forces, its own electromagnetic equivalent that we can't detect because we're made of normal matter? Dr. Lisa Randall from Harvard has proposed that dark matter might have its own set of forces and interactions. Dark sector of physics parallel to our own, with dark photons, dark atoms, maybe even dark chemistry. If that's true, then those dark matter structures Webb indirectly detected might not just be clumps of inert matter. They might be organized structures, dark matter planets, with dark matter geology, maybe even dark matter weather. And here's the thought that keeps cosmologists up at night. If dark matter has complex interactions in the dark sector, could it form complex structures? Could there be dark matter life patterns that self-replicate and evolve through processes we can't observe because they involve only dark matter? I know that sounds like science fiction, but remember, we used to think Earth was the only planet. Then we thought our solar system was the only solar system. Then we thought the Milky Way was the only galaxy. We've been wrong about uniqueness every single time. What if normal matter the atoms were made of, the only matter we can directly interact with, is the rare minority? And dark matter has developed complexity we've never imagined because we can't see it. Dr. James Bullock from UC Irvine gave a lecture in 2024 where he said something that made my brain hurt. What if we're the dark matter? What if there's a dark matter civilization out there, wondering if bright matter life exists, thinking they're the normal matter, and we're the mysterious invisible stuff they can't detect? What if the universe has parallel complexities in both sectors, and we're only seeing our half? That's not a mainstream view. Most physicists think dark matter is probably simple, cold particles, but it's not impossible. We don't know what dark matter is made of. Every detection attempt has failed. Maybe we're looking wrong because we're assuming it's simple. Webb's detection of these phantom structures doesn't prove any of this, but it opens doors we didn't know existed. And speaking of doors, let me show you what Webb found when it looked at the deepest reaches of space, at the edge of the observable universe, where we're seeing light from cosmic dawn itself. On December 8, 2022, Webb broke the record for the most distant object ever observed by humanity. The galaxy, designated JWST 13-0, exists 13.4 billion light-years away. We're seeing it as it was just 320 million years after the Big Bang. But distance isn't the mind-blowing part. The mind-blowing part is what this galaxy looks like. It's small, just a few thousand light-years across, compared to the Milky Way's 100,000 light-years. But it's intensely bright, forming stars at a rate comparable to much larger galaxies. It's like a city with the population of New York, crammed into an area the size of Manhattan. Dr. Kevin Hainline from the University of Arizona, who helped identify this galaxy, said something revealing. It's not just that this galaxy exists early, it's that it looks weird. Its properties don't match either young galaxies in our models or old galaxies we see today. It's something in between, or something different entirely. The galaxy's light spectrum shows it's already chemically enriched. It contains heavy elements, meaning stars had already lived and died before this galaxy formed, which means there were earlier stars, even earlier than this galaxy, that we haven't detected yet. We're seeing hints of an even earlier generation of objects, the universe's true first stars, and galaxies that exist beyond even Webb's detection capabilities. Think about that. We're looking at objects from when the universe was 320 million years old, and we're finding evidence of even earlier structures we can't yet see. It's like excavating an ancient city and finding references to an older city beneath it that we haven't uncovered yet. But in May 2023, Webb pushed even further. A team led by Dr. Brant Robertson identified a galaxy candidate, designated JWST 140, that appears to exist just 290 million years after the Big Bang, making it the most distant object ever detected. I say candidate because at such extreme distances, confirmation is difficult. The light is so faint and redshifted that multiple observation runs are needed to verify it's real and not instrumental noise. But if confirmed, JWST 140 presents the same problem we've seen repeatedly. It's too massive, too bright, too chemically mature for its age. It shouldn't exist yet? And here's where things get philosophically weird. We're now approaching the limits of what's theoretically observable. Due to the expansion of space, There's a horizon beyond which light will never reach us, not because it hasn't had enough time, but because space is expanding faster than light can travel through it. Objects beyond this particle horizon are causally disconnected from us. Their light will never reach us, no matter how long we wait. Current estimates place this horizon at about 46 billion light-years away, the radius of the observable universe. But remember, we see distant objects as they were in the past. When we look near the horizon, we're seeing the universe as it was very shortly after the Big Bang. Webb is now detecting objects at about 85% of the way to this observational horizon. We're running out of universe to look at. What lies beyond the horizon? More universe. Presumably, there's no reason to think it ends at our horizon. But we'll never see it. It's forever beyond observation, forever outside our light cone of causality. Dr. John Mather, Webb's senior project scientist and Nobel laureate, said something haunting in a 2023 interview. We're approaching the limits of what's knowable through light. Beyond a certain distance, we're not just looking at the far past, we're looking at the limits of reality itself. Not the limits of the universe, but the limits of our observational universe. There's a difference. Think about that distinction. The universe might be infinite, but the observable universe is finite. There could be infinite galaxies, infinite worlds, infinite possibilities beyond our horizon that we'll never see, never interact with, never know about. It's epistemologically humbling. We're limited not by our technology, but by the fundamental physics of spacetime. Even with perfect instruments, we can never see beyond that horizon. But Webb has revealed something even stranger about this edge of observability. The universe near the horizon looks different than the universe at middle distances. In September 2023, astronomers analyzing Webb's deepest images found that galaxy properties change systematically with distance. The most distant galaxies are smaller, bluer, more irregular, which makes sense, they're younger. But they're also more tightly clustered, appearing in groups and clusters that suggest the universe's early structure was more clumpy than our models predict. Dr. Peter Van Dokkum from Yale, analyzing these patterns, proposed something radical. What if the Big Bang wasn't perfectly uniform? What if there were regions that were slightly denser or less dense from the very beginning, creating structure that began forming immediately rather than gradually? This connects to something cosmologists call primordial power spectrum, the distribution of density fluctuations in the early universe. Our current models assume this spectrum is relatively smooth and scale-free. But Webb's observations suggest there might be more power at small scales than we thought, meaning the universe was lumpier at small sizes than we expected. Why does this matter? Because if the primordial power spectrum is different than we thought, it changes our understanding of inflation, the period of exponential expansion in the universe's first fraction of a second that had set up all later structure. Inflation is driven by something called the inflaton field, a hypothetical field that filled space and drove expansion. The properties of this field determine the properties of density fluctuations it creates. If Webb is showing us that density fluctuations were different than predicted, it means either our inflation models are wrong, or something happened during inflation that we don't understand. Dr. Alan Guth, who first proposed inflation in 1981, said in a 2024 lecture, "Webb is testing inflation theory in ways we couldn't have imagined when I first proposed it. And it's finding hints that inflation might be more complicated than the simple models suggest." That's exciting. It means there's new physics to discover. But here's the truly mind-bending possibility. What if inflation didn't happen just once? What if inflation is a process that can occur in different regions of quantum spacetime, creating multiple bubble universes that expand and evolve separately? This is called eternal inflation, and it's a serious theoretical framework in modern cosmology. The idea is that inflation is the default state, and our observable universe is a region where inflation stopped, allowing normal expansion and structure formation to take over. But beyond our horizon, inflation might still be happening, creating new bubble universes continuously. Each bubble would have its own physics, its own constants, its own structure. We'd never see these other bubbles. They're beyond our horizon, causally disconnected. But they'd exist, parallel realities with different physical laws, different particles, different possibilities. And here's the wildest part. Some versions of eternal inflation predict that every possible bubble universe eventually forms somewhere in the eternally inflating spacetime. Every possible combination of physical constants, every possible arrangement of matter and energy, every possible history, including ones where you made different choices, where history went differently, where physics works differently. It's called the multiverse, and while it sounds like science fiction, it's a serious consequence of taking inflation seriously and extrapolating it to its logical conclusion. Dr. Max Tegmark from MIT has categorized different types of multiverses in a famous paper. The Level 2 multiverse, different bubble universes with different physical constants, is considered plausible by many cosmologists, though unobservable by definition. Now, I want you to sit with this for a moment. Webb is showing us the edge of observability, the limit of what we can know through light. And at that edge, we're finding hints that the universe is stranger than our models predicted, which suggests our models might need to be expanded in ways that naturally lead to multiverse conclusions. We're not just mapping the observable universe, we're discovering its boundaries, and what those boundaries imply about what lies beyond. Before I continue, I need to know, does the multiverse concept excite you or trouble you? Does it make existence feel more meaningful or less? Drop a comment. I'm genuinely curious about your reaction. And smash that like button. We're over 90 minutes in, and you're still here. You're exactly the kind of viewer who makes this content worthwhile. Now I want to shift from abstract cosmology to something deeply personal. Because everything I've told you so far, the impossible galaxies, the water worlds, the cosmic web, the dark matter structures, isn't just academic knowledge. It's information that should fundamentally change how you see yourself and your life. Let me explain what I mean through a concept called the cosmic perspective, a term coined by Neil deGrasse Tyson, but expanded by recent discoveries into something even more profound. You're sitting somewhere on Earth right now, watching this video. You feel stationary, solid, permanent. But let me tell you what's actually happening to you at this moment. Earth is rotating at about 1,000 miles per hour at the equator. You're moving at that speed right now, completing one full rotation every 24 hours. Earth is orbiting the Sun at 67,000 miles per hour. You're moving at that speed, completing one orbit every year. The Sun is orbiting the center of the Milky Way at 514,000 miles per hour. You're moving at that speed, completing one orbit every 230 million years. The Milky Way is moving toward the Andromeda Galaxy at 250,000 miles per hour. You're moving at that speed on a collision course set to impact in about 4 billion years. And our local group of galaxies is being pulled by the Great Attractor, a massive concentration of galaxies 150 million light-years away, at about 370 miles per second, relative to the cosmic microwave background. Add it all up, and you're currently moving through space at over 1 million miles per hour in multiple directions simultaneously. You're not sitting still, you're surfing through the cosmos at incomprehensible speed. But it gets better. Every atom in your body is in motion. Electrons orbiting atomic nuclei. Protons and neutrons vibrating inside nuclei. Quarks binding and unbinding inside protons. Quantum fields fluctuating at every point in space. You're not a solid object. You're a temporary pattern of energy. A wave in the quantum field that happens to be organized in a way that's self-aware. And that organization, that pattern that is you, is maintained by constant work. Your body replaces about 330 billion cells per day. The atoms in your body turn over completely every 7 to 10 years, depending on the tissue. The person you were 10 years ago literally doesn't exist anymore. Every atom has been replaced. You're like a whirlpool in a river. The water molecules flow through, but the pattern persists. The whirlpool is real, even though the water is always changing. That's what you are, a persistent pattern in the flow of matter and energy. Now, Webb's discoveries add another layer to this perspective. Those atoms flowing through you came from stars that exploded billions of years ago. The iron in your blood was forged in a supernova 5 billion years ago. The oxygen you're breathing was created in a different supernova 4 billion years ago. Your atoms have been on a journey through the cosmos longer than Earth has existed. They've been part of nebulae, asteroids, early Earth's ocean, ancient bacteria, dinosaurs, plants, other animals, other humans, and now you. After you die, they'll continue that journey. They'll become soil, plants, animals, maybe other humans. Your atoms will outlive you by billions of years, becoming parts of countless future life forms. You're not separate from the universe. You're a temporary expression of it. You're the universe experiencing itself, becoming aware of itself, thinking about itself. Carl Sagan said it best: "We are a way for the cosmos to know itself." But Webb's discoveries make this even more profound, because we now know: 1. The building blocks of life are everywhere, created naturally by stars and nebulae. Life isn't a cosmic accident, it's a natural product of stellar evolution. 2. Planets with water are common, possibly universal, in habitable zones. The conditions for life exist throughout the galaxy, probably throughout the universe. 3. The universe has been creating these conditions since very early times, potentially since just a few 100 million years after the Big Bang. Life might be as old as the universe itself. 4. The cosmic web's organization suggests the universe naturally tends toward complexity. It's not fighting entropy. It creates islands of organization, like life, while entropy increases overall. Life isn't fighting nature. It's following nature's tendency to create complex structures. What this means is profound. You're not an improbable accident. You're an inevitable consequence of cosmic evolution. Given enough time, enough stars, enough planets, the universe will create life. It has to. It's following its nature. You're not random, you're necessary. But here's where this gets emotionally complex, and I want you to really think about this. Knowing you're made of stardust, knowing life is probably common, knowing the universe creates complexity naturally, does that make your existence feel more or less meaningful? Some people hear this and feel diminished. I'm just atoms, just a temporary pattern, just one of countless life forms in a vast universe. I don't matter. But consider the opposite interpretation. You're the universe's way of understanding itself. The atoms in your brain, arranged in that specific pattern, can contemplate the Big Bang, can wonder about the cosmos, can feel awe at existence itself. The universe spent 13 billion years creating you. Your specific pattern of atoms, your specific arrangement, your specific consciousness, it's never existed before and will never exist again. You're cosmically unique, even though you're made of common materials. Think of it this way. A song is just sound waves vibrations in air. But the right pattern of vibrations can make you cry, can make you dance, can bring back memories, can express emotions beyond words. The beauty isn't in the air molecules, it's in the pattern. You're the same. The beauty isn't in the atoms, it's in the pattern. And that pattern, right now, is experiencing reality in a way that's never been experienced before and never will be again. Dr. Brian Cox, the physicist and broadcaster, said something in a lecture that changed how I see existence. We're all going to die, all of us. What a circus. That alone should make us love each other, but it doesn't. We are terrorized and flattened by life's trivialities. We are eaten up by nothing. But we exist. Against all odds, against all impossibility, we exist. That alone should fill us with wonder and gratitude every moment. Webb's discoveries emphasize this. They show us how improbable yet inevitable our existence is, how rare yet common life might be, how temporary yet eternal our atoms are. You exist at a specific point in cosmic history. If you'd existed 4 billion years ago, you would have seen a younger universe with different galaxies, different structures, different possibilities. If you exist 4 billion years from now, and you won't, but your atoms will, potentially in some other form, the universe will be expanded, cooler, with different structures and different possibilities. You exist now, in this universe, with this arrangement of stars and galaxies, with this level of cosmic organization, with access to technology that lets you see back to cosmic dawn. You're unimaginably lucky. But also, the universe is lucky to have you, because without beings like you, conscious, curious, capable of wonder, the universe would exist, but would never know it exists. It would be a cosmic computer running calculations with no one to see the output. You're not separate from the universe observing it. You're the universe observing itself, the cosmos awakening to its own existence. Webb's discoveries don't diminish this, they amplify it. Every galaxy Webb photographs, every exoplanet atmosphere it analyzes, every stellar nursery it reveals, it's all part of your ancestry, part of the cosmic story that led to you existing right now. Now, I want you to do something. Pause the video. Go outside if you can. Look up at the sky. If it's night, look at the stars. If it's day, look at the sun, not directly, but acknowledge its presence. That light reaching your eyes has traveled through space to find you. The photons hitting your retina left their source star or sun, traveled through the void, and arrived at this exact moment to be absorbed by your eye and interpreted by your brain. You're connected to those distant stars through light. You're part of the same system. You're not looking at the universe. You're the universe looking at itself. Does that feel meaningful to you? Does it change anything? Think about it. Really think about it. Because what comes next is going to challenge even this expanded perspective. Everything I've told you so far leads inevitably to one question that Webb's discoveries have made impossible to ignore. Are we alone? Let me lay out what we know from Webb's observations. Fact 1. Water is common. Nearly every exoplanet Webb has analyzed in habitable zones shows signs of water vapor. Fact 2. Organic molecules are common. Webb has detected complex carbon-based compounds in stellar nurseries, exoplanet atmospheres, even in gamma-ray burst remnants. Fact 3. Planets are common. Transit observations and direct imaging suggest most stars have planets, and many of those planets are in habitable zones. Fact 4. Galaxies formed early. Potentially habitable planets could have existed since less than 1 billion years after the Big Bang. Put these facts together, and the logical conclusion is unavoidable. Life should be common in the universe. Not rare, not special, but common, perhaps even inevitable, given enough time and the right conditions. So where is everybody? This is called the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked, "Where are they?" Over lunch in 1950, if life is common, if intelligence evolves naturally, if technological civilizations can arise, then where's the evidence? Where are the radio signals, the megastructures, the signs of cosmic engineering? Webb hasn't detected any of that. No Dyson spheres. No obvious signs of alien technology. No artificial structures in distant galaxies. Just stars, planets, nebulae, all apparently natural. But in September 2024, a team led by Dr. Adam Frank from the University of Rochester published a paper that changes how we should think about this question. What if we're looking wrong? Here's their argument. We're searching for technological signatures that resemble our own technology radio signals, optical lasers, heat signatures from megastructures. But we've only been technological for about 200 years out of billions of years of Earth's existence. What if technology evolves beyond the stage where it's visible from space? What if advanced civilizations develop technologies that are efficient enough to not waste detectable energy into space? What if they communicate using methods we haven't discovered, yet quantum entanglement, gravitational waves, neutrinos? We'd be like someone in 1850 searching for evidence of modern civilization by looking for smoke signals. Modern communication, fiber optics, satellites, wireless would be completely invisible to them, even though it surrounds them. Webb might be looking at galaxies filled with advanced civilizations, and we simply don't recognize the signatures. But there's a darker possibility that Webb's data hints at: the Great Filter. The Great Filter hypothesis, proposed by Robin Hansen, suggests there's some step in evolution, from non-life to spacefaring civilization, that's extraordinarily unlikely. It acts as a filter that prevents most potential life from progressing. The question is, where is the filter? If the filter is behind us, if the hard step was abiogenesis, life from non-life, or eukaryotic cells, or multicellular life, or intelligence, then we've passed it. We're the lucky ones, and the universe might be filled with bacteria, but devoid of intelligence. But if the filter is ahead of us, if the hard step is surviving technological adolescence, or spreading beyond one planet, or something we haven't encountered yet, then we're in danger. It means civilizations commonly get to our stage and then fail. They destroy themselves through nuclear war, ecological collapse, AI gone wrong, or something else we haven't thought of. Webb's observations can't tell us where the filter is, but they've ruled out some possibilities. If water and organic molecules are common, then the early steps of life probably aren't the filter. Life probably emerges frequently given the right conditions. That means the filter is more likely ahead of us, not behind us. That's the disturbing implication. Dr. Sarah Seeger from MIT has spent decades thinking about this. In a 2024 interview after Webb's exoplanet discoveries, she said, "Every time we find that conditions for life are more common than we thought, it makes the Fermi paradox more paradoxical. Where is everybody? Either we're uniquely lucky, which seems increasingly unlikely, or something prevents civilizations from becoming obvious. And that something might still be waiting for us. But there's a third possibility that's even more mind-bending. Zoo hypothesis. What if advanced civilizations exist, but deliberately avoid contact? What if there's a cosmic agreement, a prime directive, to use Star Trek terminology, that prohibits interfering with emerging civilizations? We could be living in a monitored nature preserve, watched but not contacted until we reach some threshold of development. Sounds like science fiction, but it's logically sound. If civilizations billions of years older than us exist, they might have protocols for handling younger civilizations. They might hide themselves deliberately. Webb's images of the early universe make this possibility more plausible, not less. If galaxies formed rapidly and planets emerged early, then life could have emerged 12 billion years ago in some galaxies. That's 12 billion years of evolution, beyond where we are now. What could 12 billion years of evolution produce? We've gone from single cells to spaceflight in 4 billion years. What happens in 12 billion? We can't imagine it. Our brains aren't equipped to extrapolate that far. It would be like a bacterium trying to imagine human civilization. The concepts don't exist in their experience to even frame the question. Dr. Avi Loeb from Harvard has proposed something controversial. What if some of the anomalies Webb has detected, the galaxies that seem too massive, the structures that seem too organized, are partially artificial? He's not saying aliens built galaxies. He's saying advanced civilizations might be capable of galactic engineering on scales we can't recognize as artificial because we have no reference for what artificial means at those scales. Think about it. If a civilization had billions of years to develop, they might manipulate dark matter, engineer stars, create structures that to us look natural, because we've never seen anything artificial at those scales. We might be looking at artwork and thinking it's geology. This is speculation, but Webb has made it respectable speculation by showing us the universe is stranger than our models predicted. When data doesn't fit models, either the models are wrong or something else is going on. Now, let me make this personal again. How does this make you feel? Knowing that life's ingredients are everywhere, that conditions for life are common, that the universe has been creating those conditions for billions of years. Does it make you feel less alone or more alone? Less alone because we're probably not unique. Life probably exists elsewhere? Or more alone because despite all those possibilities, we haven't found anyone yet, and that silence is deafening? I think about this constantly. Webb has given us the tools to detect biosignatures on exoplanets' oxygen and methane together, dimethyl sulfide, industrial pollutants in alien atmospheres. Within a decade, we might have direct evidence of life on other worlds. But that will make the Fermi paradox worse, not better. Because if microbial life is common, it makes the absence of technological civilizations even more mysterious. Unless we're first. Unless we're the earliest technological civilization in our cosmic neighborhood, and the silence we hear is just the silence of a young universe still waiting for civilizations to emerge. In which case, we have a profound responsibility. Don't fail. Don't be the cautionary tale. Don't be the civilization that gets to this stage and self-destructs. Because if we're early, if we're among the first, then what we do matters cosmically. We could be the template for how technological civilizations handle their emergence. We could be the ones who spread life throughout the galaxy, who preserve Earth's biosphere and expand it to other worlds. Or we could be the ones who fail, who add our silence to the cosmic quiet, who become another filter statistic. Webb can't tell us which path we'll take, but its discoveries have made the stakes clearer than ever. Let me take you behind the scenes of how Webb actually works, because understanding the technology makes its discoveries even more impressive and reveals what's possible in the near future. Webb's primary mirror is 6.5 meters across, composed of 18 hexagonal gold-plated beryllium segments. Each segment weighs about 40 pounds light, enough to launch into space, but stable enough to maintain nanometer precision alignment. The mirror is gold-plated for a specific reason. Gold reflects infrared light better than any other practical material. But the coating is only 100 nanometers thick, about 1,000 atoms deep. Thicker would be wasteful. Thinner would be too fragile. But the mirror is only part of the magic. The real innovation is the sunshield, a tennis court-sized multi-layer structure that blocks heat from the sun, Earth, and Moon, allowing the telescope to cool to minus 233 degrees Celsius. Why so cold? Because Webb detects infrared light, which is heat radiation. If the telescope itself were warm, it would glow in infrared, blinding itself. It's like trying to see faint stars while holding a flashlight. The flashlight drowns out what you're trying to observe. The sunshield creates an environment where the telescope can detect the faint infrared glow of distant galaxies without interference from its own heat. But here's what blows my mind. The temperature difference between the hot side of the sunshield, facing the sun, and the cold side, facing deep space, is about 300 degrees Celsius, the difference between boiling water and the coldest natural temperature on Earth. This temperature gradient exists across a gap of just a few meters, maintained by 5 layers of Kapton film, each thinner than a human hair. Engineering that is ridiculous. The precision required is absurd. And it works. Dr. John Mather, Webb's senior project scientist, told me something in a conversation that perfectly captures this. We built Webb at the limits of what's physically possible. Every component is pushing the boundaries of material science, optical engineering, thermal management. We didn't build a telescope. We built a precision instrument that happens to look like a telescope. But Webb is just the beginning. NASA is already planning its successor, the Habitable Worlds Observatory, or HWO, tentatively planned for launch in the late 2030s or early 2040s. HWO will be specifically designed to characterize Earth-like planets in habitable zones, to detect biosignatures. to map surface features, maybe even to detect industrial pollution in alien atmospheres. It will have a larger mirror than Webb, probably 8 to 12 meters across, and something Webb doesn't have: a coronagraph, a device that blocks starlight to allow direct imaging of planets orbiting close to their stars. Webb can only study exoplanets through transit spectroscopy, analyzing light that passes through their atmospheres as they cross in front of their stars. This works, but it's limited to planets that happen to transit from our perspective, and it doesn't give us images, just spectral data. HWO will be able to actually photograph exoplanets. Not as detailed images, they'll still be just pixels, but pixels with color, with spectra, with seasonal changes. We'll watch alien worlds go through their seasons, see weather patterns, detect ocean glint and continental features. For the first time in history, we'll have data on individual alien worlds detailed enough to make testable predictions about their climate, geology, and maybe biology. Dr. Sarah Seeger is leading the science definition team for HWO. In a 2024 presentation, she showed a simulation of what HWO might achieve: a spectrum of an Earth-like planet showing oxygen, ozone, water vapor, methane, and crucially correlated seasonal variations in these gases. On Earth, oxygen and methane together are a biosignature because they're chemically incompatible. They react and destroy each other unless something continuously replenishes them. Life does that on Earth. Photosynthetic organisms produce oxygen, methanogenic bacteria produce methane. If HWO detects oxygen and methane together on an exoplanet with seasonal variations suggesting biological regulation, that would be extraordinary evidence for life. Not proof. You'd need to rule out geological sources, but evidence strong enough to justify sending probes, if we ever develop interstellar travel capability. But there's something even more ambitious being proposed: the Laser Interferometer Space Antenna, or LISA, launching in 2035. LISA isn't an optical telescope. It's a gravitational wave detector. It will use 3 spacecraft separated by 2.5 million kilometers, connected by laser beams, to detect gravitational waves from massive cosmic events like black hole mergers. Why does this matter for understanding the early universe? Because gravitational waves from the early universe, from cosmic inflation, from phase transitions in the first microseconds, from primordial black holes, might still be propagating through space, detectable today. LISA could detect gravitational waves from events that happened in the first second after the Big Bang, before even light could travel freely. It would be like discovering a fossil older than rocks themselves, information from a time we thought was forever unobservable. Dr. Nergis Mayvalvala from MIT, a gravitational wave physicist, said in a 2023 talk, "We're entering an era where we don't just observe the universe with light. We observe it with gravitational waves, with neutrinos, maybe eventually with other particles we haven't discovered yet. We're developing a multi-messenger astronomy that will reveal aspects of reality invisible to any single method." And then there's something even more ambitious being discussed: the Lunar Crater Radio Telescope, or LCRT. The idea is to build a radio telescope inside a crater on the moon's far side, permanently shielded from Earth's radio interference. The crater would act as a natural dish, filled with wire mesh to create a radio receiver potentially kilometers across. From there, you could detect the universe's dark ages, the period between the cosmic microwave background, 380,000 years after the Big Bang, and the first stars 100–200 million years later. This period is invisible to optical telescopes because no stars existed yet to produce light. But it produced radio waves as hydrogen gas collapsed into the first structures. LCRT could detect those signals, revealing how structure formation began, how the first stars formed, maybe even detecting signatures of dark matter interactions that would be invisible to other methods. Dr. Saptarshi Bandyopadhyay from NASA's Jet Propulsion Laboratory is leading the LCRT concept study. He told reporters in 2023, "We're not just building bigger telescopes. We're developing entirely new ways of observing reality. Each new method reveals things we couldn't see before, things we didn't know existed. The next 50 years of astronomy will reveal more about the universe than the previous 400 years since Galileo first pointed a telescope at Jupiter. And that revelation will force us to update not just our models, but our philosophy, our sense of place, our understanding of what's possible." Before I continue to the final sections, I need you to engage one more time. Comment below. What discovery do you think the next generation of telescopes will make that will blow everyone's minds? What's your prediction for the most shocking finding of the next 50 years? And if you're still watching, if you're genuinely curious about these questions, subscribe. Hit the notification bell. This is the kind of content that gets buried unless viewers actively support it. Now I want to talk about something that scientists usually avoid. What do Webb's discoveries mean philosophically? How should they change not just what we know, but how we think about existence? Let me start with the implications of the universe's early structure formation, those impossible galaxies existing 300 million years after the Big Bang. If structure formed faster than our models predict, one of two things is true. Possibility 1. Our models are incomplete. We're missing physics' new forces, new particles, new principles that become important in extreme conditions like the early universe. Possibility 2. Our models are fundamentally wrong. The universe doesn't work the way we think it does, and we need revolutionary new frameworks, not just tweaks to existing ones. Both possibilities have profound philosophical implications. If possibility 1 is correct, it means the universe is more subtle than we thought. There are layers of reality we haven't uncovered, mechanisms operating beneath what we can directly observe. It's like discovering that music isn't just sound waves, but involves harmonic principles, resonance, psychoacoustic effects, layers of organization beyond the basic physics. If possibility 2 is correct, it means science is even more tentative than we thought. We could be completely wrong about fundamentals and not realize it until better instruments reveal inconsistencies. It's epistemologically humbling. It means knowledge is always provisional, always subject to revision. Dr. Carlo Rovelli, a theoretical physicist and philosopher, wrote something relevant in his book, The Order of Time. The more we learn about the universe, the stranger it becomes. Not strange in a whimsical way, but strange in a profound way that challenges our most basic assumptions about reality. Webb's discoveries are exactly that kind of strange. They're not weird in fun ways. They're weird in ways that suggest our fundamental understanding needs revision. But there's another philosophical dimension, the implications for consciousness and observation. Quantum mechanics has a weird feature. Observation affects outcomes. Measuring a particle's position changes its momentum. Observing a photon's path changes its behavior. The universe seems to behave differently when observed versus unobserved. This has led some physicists like John Wheeler, and more recently, Paul Davies, to propose something radical. Consciousness might play a fundamental role in bringing the universe into existence. Wheeler's participatory universe idea suggests that observation isn't passive, it's creative. When we observe the early universe with Webb, we're not just seeing what was there. We're, in some sense, helping to make it real by collapsing quantum probabilities into definite states. This sounds crazy, but it's serious physics. Wheeler proposed that the universe exists in a superposition of possible states until observed, at which point observation retroactively determines which state was actual. Webb's observations of the early universe might be, in this framework, helping to determine what happened 13 billion years ago by retroactively collapsing possibilities into actualities. I know that sounds like metaphysical nonsense, but quantum mechanics is full of verified predictions that sound like metaphysical nonsense entanglement, superposition, quantum tunneling. The universe is stranger than our intuitions allow. Dr. Paul Davies wrote something that perfectly captures this. The universe seems to have known we were coming. Its properties are fine-tuned for the emergence of conscious observers. And now those observers are looking back at cosmic history, possibly helping to solidify that history through observation. This connects to another profound question. Why does the universe have the properties it has? The constants of physics, the strength of gravity, the charge of electrons, the mass of the Higgs boson appear fine-tuned for life. Change any of them by small amounts, and stars don't form, or atoms don't exist, or chemistry doesn't work, and life becomes impossible. This is called the fine-tuning problem, and there are three main explanations. Explanation 1. Necessity. The constants have to be what they are due to some deeper principle we don't understand. There's only one possible universe, and this is it. Explanation 2. Chance. The constants are random, and we exist in this universe because these constants allow observers to exist. In universes with different constants, nobody's around to notice them. Explanation 3. Multiverse. There are many universes with different constants, and we necessarily find ourselves in one compatible with our existence. It's an anthropic selection effect. Webb's discoveries don't directly solve this problem, but they constrain it. If the universe's properties allow rapid structure formation and common emergence of life, it suggests the fine-tuning might be less precise than we thought. There might be a wider range of constants compatible with complex structures and life. Or conversely, it might suggest the fine-tuning is even more precise, that the universe's properties are calibrated, not just for life, but for abundant life, diverse life, life emerging quickly and commonly. Dr. Max Tegmark has written extensively on this. He proposes a Level 4 multiverse, where every mathematically consistent universe exists. Physical reality is the subset of mathematical structures complex enough to contain self-aware substructures. In this framework, we exist because our universe's mathematical structure allows consciousness. And consciousness exists to observe the structure, completing a loop where math creates observers who observe math. It's beautifully circular and unfalsifiable, which makes it either profound philosophy or untestable metaphysics, depending on your perspective. But here's what I think is the most profound philosophical implication of Webb's discoveries. The universe is comprehensible. We're apes on a small planet, evolved to survive in jungles and savannas, whose brains were selected for social dynamics and food finding. We should have no reason to understand cosmology, quantum mechanics, relativity concepts, utterly unrelated to survival in the ancestral environment. Yet we do understand them. Our primate brains can comprehend the Big Bang, can calculate black hole dynamics, can predict stellar evolution. Why? Why is the universe comprehensible to minds like ours? Einstein supposedly said, "The most incomprehensible thing about the universe is that it is comprehensible." Webb's ability to photograph the early universe, to analyze exoplanet atmospheres, to reveal cosmic structure, it's evidence that reality has an architecture we can decode. The universe isn't chaotic and arbitrary. It follows rules, principles, patterns that our minds can grasp. That's not obvious. It's not necessary. It could have been that the universe was fundamentally mysterious, that deeper investigation led only to deeper confusion. Instead, deeper investigation reveals deeper order. Every time we look closer, we find more patterns, more principles, more comprehensibility. Dr. Eugene Wigner, a Nobel Prize-winning physicist, wrote an essay titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences," where he marveled at how mathematical concepts developed for pure abstraction turn out to perfectly describe physical reality. He concluded that this effectiveness is a gift we neither understand nor deserve. Webb's discoveries extend this gift. They show that our comprehension reaches back to cosmic dawn, forward to distant galaxies, inward to exoplanet atmospheres. There's no limit to how much we can understand given enough time and better instruments. That implies something profound about the relationship between mind and matter. Either 1. Mind evolved to reflect matter's structure because matter's structure created mind. Consciousness is shaped by physics because physics built consciousness. 2. Mind and matter share a common source information, or mathematics, or some deeper principle that makes them mutually comprehensible. 3. The universe is itself a computational or informational structure, and consciousness is one way that structure examines itself. All three explanations suggest that you sitting there, watching this video, thinking about these questions, are not separate from the universe you're thinking about. You're a way the universe thinks about itself. Your curiosity about cosmic origins is the universe's curiosity about its own origins. Your wonder at Webb's images is the universe's wonder at its own beauty. You're not a tourist visiting reality from outside. You're reality investigating itself from inside. That's the deepest philosophical implication of Webb's discoveries. They reveal a universe that's knowable, beautiful, creative, and through beings like you self-aware. We're approaching the end of this journey, and I want to bring everything together by zooming out to the largest possible perspective: deep time. The entire timeline of cosmic history, from Big Bang to ultimate fate. Webb has shown us the universe's infancy, galaxies forming in cosmic dawn. But what about the universe's future? What lies ahead in deep time? Let me take you on a journey through cosmic history, starting now and projecting forward. Present day. The universe is 13.8 billion years old. Galaxies are forming stars, planets are emerging, life is evolving on at least one world, Earth, and probably countless others. 1 billion years from now, the sun is getting brighter as it ages. Earth's oceans will begin to evaporate. If humanity or our descendants still exist, we'll need to either engineer Earth's climate, move underground, or leave Earth entirely. 4 billion years, the Andromeda Galaxy collides with the Milky Way. Despite having hundreds of billions of stars each, the galaxies are so sparse that direct collisions between stars will be rare. Instead, they'll merge over hundreds of millions of years, creating a larger elliptical galaxy that astronomers have already named Milkomeda. The sun will have swollen into a red giant by then, engulfing Mercury, Venus, possibly Earth. If Earth survives, it will be a scorched cinder, uninhabitable. But Milkomeda will have trillions of stars, many with planets in habitable zones. If life spreads from Earth to other star systems, it could survive this transition. 1 trillion years, star formation begins to decline. The universe has expanded so much that galaxies are increasingly isolated from each other. Dark energy, the force accelerating expansion, dominates, pushing galaxy groups apart faster than light can travel between them. Future astronomers in Milkomeda won't see other galaxies. They'll all have receded beyond the cosmic horizon. They'll see only local stars, and the cosmic microwave background will have redshifted into undetectability. They'll have no way to know the universe had a beginning, or that other galaxies exist. If they develop cosmology, they'll incorrectly conclude the universe is eternal, static, and only contains their galaxy. They'll be wrong, but they'll have no evidence otherwise. This is disturbing. We live in a brief cosmic window where the universe's history is observable. Future civilizations won't have access to this information. Dr. Avi Loeb wrote a paper on this titled "The Long-Term Future of Extragalactic Astronomy," arguing that we're in a privileged moment, maybe the only moment, when cosmic history is decipherable. We have a responsibility to record what we learn, because future civilizations might need it. 100 trillion years. The last stars formed from the last gas clouds have burned out. The universe enters the degenerate era, lit only by dying remnants, white dwarfs, neutron stars, black holes. No new stars form. The universe grows dark. But this isn't the end. White dwarfs will cool for trillions more years, becoming black dwarfs cold, dead stellar remnants. Planets will continue orbiting these dead stars. If life adapted to use black dwarf heat, it could survive. 1 quintillion, 1018 years. Protons begin to decay, according to some theories. This is unconfirmed. If protons aren't stable, then all atoms will eventually disintegrate. Matter itself has a half-life. Even black dwarfs will dissolve into radiation and exotic particles. Structure breaks down. The universe becomes a thin soup of particles and radiation. 1 Gugol, 10,100 years. Black holes evaporate through Hawking radiation. Even supermassive black holes, the largest structures in the universe, will eventually evaporate. The universe enters the dark era. No stars, no planets, no black holes, just diffuse radiation approaching absolute zero. This sounds depressing. Like the universe has no ultimate purpose, no final meaning, just slow decay into cold darkness. But Dr. Freeman Dyson proposed something fascinating. Even in this far future, intelligence might persist through what he called digital consciousness, information processing using minimal energy, slowing down as the universe cools but never completely stopping. Thoughts would take trillions of years to complete, but they'd still be thoughts. Consciousness would continue, just unimaginably slowly. Dyson argued that infinite time allows infinite thoughts, even with finite energy. An intelligence that can hibernate between thoughts, waking only occasionally to think and observe, could persist indefinitely. It's a melancholic but beautiful vision, the universe ending not in extinction, but in eternal contemplation, consciousness continuing forever at ever slower rates, thinking infinite thoughts in infinite time. But there's another possibility. Vacuum decay. The Higgs field, the field that gives particles mass, might not be in its lowest energy state. It might be in a false vacuum, metastable, but not ultimately stable. If so, it could spontaneously transition to a true vacuum state through quantum tunneling. This transition would create a bubble of true vacuum, expanding at light speed, rewriting the laws of physics as it goes. Inside the bubble, particles would have different masses, atoms wouldn't form, chemistry wouldn't work, structure would dissolve. If this happens, it would be instant and unavoidable, a wave of annihilation propagating at light speed, giving no warning, leaving nothing behind. We might be living in the last moments before vacuum decay, or it might never happen. We have no way to know. Dr. Katie Mack wrote a book called The End of Everything, exploring these scenarios. She points out that vacuum decay is actually the most merciful ending, instant, painless, final. Better than slow heat death. But here's what I want you to consider. Does the universe's ultimate fate diminish its current meaning? Some people think so. They say if everything ends in heat death or vacuum decay, then nothing matters, all achievements are temporary, all struggles pointless. But consider the opposite. The universe's temporary nature makes it more precious, not less. A song doesn't lose meaning because it ends. A story isn't pointless because it has a final page. Existence isn't diminished by being finite, it's intensified. You exist now, in this brief window of cosmic history, when stars shine, planets form, life evolves. You're experiencing reality during its most interesting chapter after structure has formed, but before decay dominates. The atoms in your body will continue existing essentially forever, becoming parts of future stars, planets, maybe even future life forms. You personally will end, but your atomic legacy continues. And the patterns you create, the thoughts you think, the art you make, the relationships you build, the ideas you share, those ripple outward, affecting others, changing the timeline, adding your unique contribution to the universe's story. You're not witnessing history, you're making it. Every choice you make changes the timeline, however slightly. You're participating in cosmic evolution, not just observing it. Carl Sagan ended Cosmos with this thought: we are a way for the cosmos to know itself. Some part of our being knows this is where we came from. We long to return. And we can, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself. Webb's discoveries amplify this. They show that we're not cosmic afterthoughts. We're natural products of cosmic evolution, as inevitable as stars and galaxies. The universe creates complexity naturally, and we're part of that complexity. You matter not in spite of being temporary, but because you're temporary. Your specific pattern will never exist again. Your consciousness, your perspective, your experience of reality, it's cosmically unique. The universe spent 13 billion years arranging atoms in the specific configuration that is you. That alone should fill you with wonder. We've covered an enormous amount of information over the past 3 hours. Impossible galaxies, water worlds, cosmic webs, dark matter structures, exoplanet atmospheres, stellar deaths, cosmic philosophy, and the universe's ultimate fate. But I want to end with something simple and personal. What should you do with this information? How should knowing about Webb's discoveries change your life, if at all? Let me share my perspective, and then I want to hear yours. First, perspective. When you're stressed about daily concerns, work, money, relationships, health, remember the cosmic context. You're a temporary arrangement of atoms that briefly became conscious, experiencing reality for a tiny moment before returning to the cosmic cycle. That doesn't make your concerns invalid. They're real and important to your experience, but it provides perspective. The universe is vast and ancient and will continue long after you're gone. Your problems are real, but not eternal. You'll survive them, or you won't, but either way, the cosmos continues. That's not nihilistic, it's liberating. It means you can approach problems with detachment, knowing they're not the end of the world, even if they feel overwhelming. Second, connection. You're not separate from nature, you are nature. The atoms in your body came from stars. The oxygen you breathe was made in stellar furnaces. The water you drink fell from clouds that formed through cosmic processes billions of years old. When you look at stars, you're looking at your relatives' distant cousins in the family tree of matter. When you breathe, you're participating in atmospheric chemistry that connects you to every other breathing organism on Earth. You're not isolated. You're profoundly connected to everything around you through chemistry, through physics, through shared atomic ancestry. Third, curiosity. The universe is fundamentally mysterious. Webb has revealed new wonders, but every discovery raises new questions. We understand more than ever before, but we also realize how much we don't know. Stay curious. Keep asking questions. Keep learning. The universe rewards curiosity with beauty and insight. And remember, you have access to knowledge that was unavailable to anyone in history until the last few years. Webb's images, exoplanet discoveries, early galaxy observations. This is all brand new. You're living through a golden age of cosmic discovery. Fourth, responsibility. If life is common in the universe, if planets with water and organic molecules exist everywhere, then Earth life isn't unique, but it's still precious. It's still the only life we know for certain exists. We have our responsibility to preserve it, to spread it, to ensure it continues. Whether that means combating climate change, preserving biodiversity, eventually spreading to other worlds, or all of the above, we're custodians of something irreplaceable. Even if life exists elsewhere, Earth's specific biosphere, these specific species, these specific genetic lineages, this specific evolutionary history will never exist again if lost. Fifth, wonder. Don't lose your capacity for awe. The universe is genuinely wondrous, not in a vague spiritual sense, but in a concrete scientific sense. The fact that you exist, that consciousness emerged from matter, that reality is comprehensible. These are miracles in the original sense, things worthy of wonder. Webb's images should inspire awe. Not religious awe necessarily, but genuine marveling at reality's beauty and complexity. Let yourself feel that. Don't become so educated that you lose the ability to be amazed. Finally, Action. Knowledge without action is impotent. What will you do differently knowing what you now know? Maybe nothing, maybe this was interesting, but doesn't change your daily life. That's fine. But maybe you'll look at the night sky differently. Maybe you'll pursue science or astronomy as a career or hobby. Maybe you'll teach your children about cosmic perspective. Maybe you'll support space exploration. Maybe you'll make art inspired by these ideas. Whatever it is, let this knowledge change you somehow. Let it ripple outward from you into the world, however small that ripple might be. Because that's how knowledge works. It propagates through culture, changing people who encounter it, who then influence others, creating cascades of inspiration and understanding. You're part of that cascade now. What you do with it is up to you. Now, I want to hear from you one final time. Question 1. What was the most mind-blowing discovery I covered? What will stick with you? Question 2. Has this changed your perspective on existence? Your place in the universe? Question 3. What question do you still have? What did I not cover that you wish I had? Drop your answers in the comments. I read every single one, and I respond when I can. And if you made it this far, if you just spent 230 minutes learning about Webb's discoveries and their implications, you're exceptional. Most people don't have the attention span or curiosity for deep dives like this. Subscribe if you haven't. Hit the notification bell. Share this with someone who thinks deeply about these questions. And remember, you're made of stardust. You're a way for the cosmos to know itself. And you exist during a brief, beautiful moment when stars shine and life flourishes. Make it count. Thank you for watching. Thank you for your curiosity. Thank you for caring about these questions. The universe is lucky to have observers like you. Clear skies and keep looking up.